Hello everyone, we'll continue with the next 5 organic questions of the NET 2022 September question paper, right? So let's start with the question number 11. I'm doing only the organic questions. The reagents A and major product B in the following reaction sequence are. So they have made this, they have given this aldehyde, which of course is an alpha beta unsaturated aldehyde. They're asking what is the reagent A, so that you get this product, and then you're reacting with CS3CHO. So it's acetaldehyde, and in presence of acid, and they're asking what's product B. So for A, let us see what are the choices they're given. The choices are NaBH4 followed by H2S and catalytic pyridine, and here it is H2S followed by catalytic pyridine. Here it is again H2S followed by catalytic pyridine, and NaBH4 followed by H2S and catalytic pyridine. So basically we have two choices. Either you add first NaBH4 and then you add H2S, or you add first H2S and then second step you add NaBH4. Now very clearly this is alpha beta unsaturated ketone. So how does it look like? It is like this, right? Now you have alkene. Now if you have to add H2S, it has to undergo 1,4 addition. If you are able to add basically SH minus is at the finally. So let us think as SH minus. So only when it gets added here, this reaction can happen, so that you are getting SH here, right? It's not possible if this OH is reduced. NaBH4 is a mild reducing agent, will reduce the aldehyde and ketone and will make into alcohol. Once it becomes alcohol, this addition is not possible. So clearly option A and option D is not possible, because first we cannot reduce and the this one. So of course the first step is you add H2S in presence of catalytic pyridine. So that should be very simple. So H2S goes and attacks here, this comes up, O minus picks up proton, or pyridine is a pyridine will help to take out the proton, and you get this. Apart from that you get ketoenol. So ketoenol will tautomerize back to your aldehyde. So basically this lone pair of oxygen actually comes down first, and the sigma bond is lost later, and this comes up and it picks up this proton, and then in this oxygen has positive charge, it comes back. So you get this ketoenol tautomerization. Now what's the next? Next they are asking you add acetaldehyde in presence of acid H plus. So this should be very simple. It's like 1,3 diol is there, position number, you see this 1, 2 and 3. So if you add acetaldehyde, it will go and form if you add aldehyde to it, to a 1,3 diol, it will go and form acetal. So very similar to acetal, it will be like half thioacetal, half acetal part in presence of acid. So all of the product you see, they are showing the same acetal formation. What we need to see is the stereochemistry of the product formed. So let us see this. So it's very simple. Acetaldehyde, it's not electrophilic enough. Aldehydes are not electrophilic enough. That's why you need acid catalyst. So this oxygen goes and attacks this proton. You get positive charge. Then this sulfur will go and attack here, because sulfur is more powerful nucleophile than oxygen. That's why sulfur will attack here. This comes here. Then this picks up proton. Now this is what is very important. Acetal formation, it is never SN2 reaction. All the steps are SN1 reaction, and they are reversible in nature. Now we could have thought that this oxygen goes and attacks here, and this leaves. That would have been SN2 reaction. SN2 reaction is never seen in acetal formation. What is seen is sulfur goes and attacks here, and this gets out, and you get, it's not exactly carbocation, but thionium ion, you can say. Something like if oxygen was there, you would have called oxonium ion. Here it is sulfur, so it will be thionium ion. So it's kind of carbocation, because it will have two chemical structures. If you remove this, you get positive charge here, and sulfur will be neutral. So SN1 reaction, then this goes and attacks here and you get this. Now what we need to understand is this reaction is reversible at every step. So it is thermodynamically controlled. That means every step it will go, it goes back. Once it goes back, it will come back, goes back to reactant, comes as product. It will go and form the most stable product, right? Thermodynamically most stable product. So that's for when it goes and comes back, the most stable product will be both PR and CH3 will be in the equatorial position. And they are position number 1, 2, 3. 1, 2, and 3. That means CS3 is below the plane, PR is also below the plane. So when you draw, you can draw both of them away from the viewer. If you rotate, you will see that they both are towards the viewer also. So they both are basically in the same plane. So of course, answer cannot be this one. Sorry, this is anyway lost. Answer cannot be this one because propyl and methyl group has to be in the same plane. So answer is your option number yeah, option number C, right? So once again, I'll go very slowly. Please go through whatever I've written. Pause it if it goes little fast. Yeah, moving on to the next question. The question says the intermediate involved in the following reaction is R. So this was quite tough question. Looks very simple, but it took pretty long time for me to solve this question. So you have this molecule which has a 4-member ring. Very clearly this should open up first because very unstable in heat. So whenever you see some double bonds and heat or light, you know it is pericyclic reaction. Okay, so what happens is and these are the intermediates which are seen. So we know it is four-membered ring, and ring opening or ring closure can happen because it is closed ring, so it will ring open. And then you can see 4 pi bonds are there, 1, 2, 3, 4. You can see the number of electrons involved in rotation is this sigma bond, so 2 electrons plus this pi bond, so it is 4 electrons. Now 4 electrons, con rotation is this. You have to remember, you can always use FMO and find out, but no need to do, you just remember one simple thing, 4n 4n h nu is this. I'm so sorry. Okay, I have written here this, but it is actually con. 4n h nu is this. So 4n thermal is con, right? Actually here I have written correctly con. Here by mistake I wrote of this, it will be con. Okay, so it's con rotation. Right now it really does not matter because it's all about ring opening, and you have no stereochemistry left because at the end you are getting 2 hydrogens here. This is also hydrogen. Okay, so we don't get the stereochemical outcome of it. All we understand is this ring opens up like that, and we get this. Yeah, and then what happens is next step looks like, because it is 4n plus 2, right? So because 6 electrons are there, 2 electrons here, 2 electrons here, 2 electrons, so 6. So 6 pi electrons are there, so 6 is not 4n. 4n plus 2 where n is equal to 1, so 4 into 1 is 4 plus 2 is 6. So now 4n h nu is this, 4n plus 2 thermal is, sorry, 4n thermal is gone. So if 4n h nu is this, so 4n plus 2 h nu will be gone, and 4n plus 2 thermal is gone, so 4n plus 2 4n plus 2 4n plus 2, thermal will be this. Okay, thermal will be this, right? So what happens here is, this one rotates. Now we have to think. Yeah, so this looks very very simple, because again stereochemistry is not involved, because in the product only they are given. This gives the right product. But interestingly, this intermediate is not given in any of the options. You see, none of the option gives this. So very clearly this is not the answer what they are looking for, though it is not wrong. Okay, ultimate gives this. So what you have to understand is, initially it gives this con rotation and gives this. This intermediate is not of great significance because no stereochemistry is involved. They are asking for stereochemistry of the further. Now what happens, please understand, there are two kinds of system possible. 4n system also was possible, and 4n plus 2 system was also possible. We saw the 4n plus 2. But 4n system is kinetically more favored. Now 4n h nu is this, that means 4n thermal is con. Okay, 4n thermal is con. So first what happens is, con rotation. Yeah. So first what happens, this electrocyclic reaction occurs by con rotation. Now what is con? Con means both the bonds, they will rotate clockwise or both will rotate anti-clockwise. So reaction is simple. This goes here, this pi bond comes here, this pi bond comes here, and you get a 4-membered ring. And rotation occurs clockwise. So imagine you're rotating this clockwise. Okay. So this hydrogen was in plane and this CH3 is also in plane. So if I rotate it like that, you understand, 90 degrees I am rotating. So what is happening? Basically H is coming down, CH3 is coming front. 90 degrees. Okay. So perfectly CH3 will come up and H will go down. That's what I have shown here. And here what happens? Here also same thing. On this double bond you see. So I am looking at only this bond. This bond I am rotating. Okay. So this double bond, one is this allyl group and one is this hydrogen. So when I am rotating 90 degrees, what is happening? H is coming front and this allyl part is going down. So that's what H I am not showing. Allyl part has gone down. I hope I made sense. Please look into it. Think about it. Once you understand, then only you move ahead. Okay. I have rotated both of them 90 degrees. I have rotated both of them 90 degrees. So 90 degrees. So H comes front like that. Okay. And similarly here also I have rotated like that. So this was in the plane. So when I rotate it up, CH3 comes outside the screen. H goes inside the screen. Okay. And so you get this. This is one of the intermediate which they have shown. Further what happens is, again it opens up. Okay, again it opens up. So now once again when it opens, it is again con rotation. So this comes here, this comes here, again it is same. So this again we are showing both of them are rotating clockwise. So this time I have drawn orbital so that it makes more sense. Maybe I could have drawn, yeah, here I could not draw the orbitals, but something I could have drawn like that. Okay, this is the orbital. So one is plus and one is minus. So down is plus and this is minus. So this rotates like that 90 degrees, this rotate like that 90 degrees, so that they meet plus plus and form the sigma bond. So because they both are rotating that side clockwise, you are getting this one. Now here what happens? Now bond is formed. That means of course plus plus is interactor, minus minus are far from each other, or minus minus interactor, plus plus are far from each other. So now when I am rotating 90 degrees, so what happens? This CH3 goes in the plane. You understand? This CH3 is coming outside the screen, exactly on your face it is coming, and this H is going inside the screen. So when you are rotating 90 degrees, CH3 is coming up and hydrogen is coming down. You can see CH is going up, hydrogen is coming down. Similarly this also, when I rotate, what happens? See, H is going up and allyl group is coming down. And then after that it's very very simple, no stereochemistry involved, so we don't bother about it. So further now it is 4n plus 2, so this rotates here, this rotates here, this rotates here, and you get this. Okay, so you can ask why, one sec, yeah, you can ask this question that why it has to close and then again open, because here this pi bond and this pi bond, they were far from each other, right? So if it has to form a six membered ring like 4n plus 2, they have to be next to each other, they have to be like this. When it is away from here, they cannot form. You can see there is no possibility of forming six membered ring. Therefore first it closes, then it opens again, so that because that rotation, now you see this h is up and this part is below, right? Here what was happening, this part was up and h is below, so a reaction cannot happen. So twice it rotates in the same way, so that comes in the correct stereochemistry, and then this reaction occurs. Okay, I'll go once again from the top, please read it thoroughly. So you can see here I have written here, the system is not strained and thus lead to product formation. Right, so the answer was option number B. Moving on to the next question. Question says the intermediate involved in the following reactions are. So you are having this molecule. This is metathesis reaction. It's a very simple, very easy reaction and very interesting reaction. They got Nobel Prize for it. So just what you do is basically you cut off this part and you join off the thing which has the metal on it. That's what is metathesis all about. And then second, once again that will happen, and basically new part gets out and the ruthenium takes its own alkene part and goes. So that's what the intermediate they're asking. This was very very simple question. So what happens is whenever you such a reaction is there, always put ruthenium in the inside part, because then only ruthenium will go and join. The other part has to break. Please understand, in the terminal alkene the terminal part has to get out and the inside part has to go and join the ruthenium. So ruthenium has to be inside, this has to go inside. You cannot do something like this, pH and ruthenium outside, and you do something like this reaction. Okay, you cannot do this, it does not happen. Okay, so you cut it, means it must be happening, but once you do that mechanism, you put your pen and paper and see, you'll get the exactly same product as the reactant. So that does not give you favorable reaction. Reaction will stop there. So again, whatever goes in the same will again go here, this what we have shown, and that gives you the required product. Okay, so this alkene comes and attacks here, and this bond comes and attacks here, and you're getting four membered ring. Now this will undergo elimination reaction, so the ruthenium comes to alkene of parent compound. So now this opens up, this opens, and you get ruthenium here. Again you understand, this part has to get out, only the inside part will form the ring. So the whatever has to get out, now this part goes and attacks the ruthenium, this comes here, so that you get this, and then this will break up and you are getting this ring and you are getting this. So the answer is option D, intermediates A and B. Now let's see question number 14. Consider the rate law. Rate is equal to K into epoxide for the reaction shown below. The plausible intermediate is, so you are having this molecule and you're reacting with alkene and you're getting this product, and these are the options, right? What they are asking is possible intermediate. So rate law, what it says is rate is equal to K into epoxide. That means this reaction depends only on the epoxide concentration, not on this. So this is the slow step. So first step is, of course, it will break. Now there are two possibilities. It can break from 1, what I have shown, or it can break from 2, right? Apart from that, very important thing is CO bond is weaker than CC bond any given day. CO bond is 69 kilocalories, whereas CC bond is 71 kilocalories. So CO bond cleavage looks obvious option, right? In epoxide, if its concentration, if the reaction depends on the concentration of epoxide, epoxide only will react, right, in the intermediate step. So this cannot break CC bond. If it breaks, everything goes off. But you should know why it does not break, because CO bond is much weaker than your CC bond. Now when this opens, what do you see? You get positive charge here, you get negative charge here. Whereas from 2, when it opens, you get positive charge here, negative charge here. Now you understand, Cn is an electron withdrawing group by minus R effect, minus I effect both. You give positive charge, highly unstable. O minus anyway does not make much difference. But by here, if you see, you are having positive charge here and you are having benzene ring. pH is your phenyl ring, right? Now phenyl ring can donate electrons. Phenyl ring can donate electrons and stabilize this carbocation so that positive charge delocalized over 4 carbon atoms. So like each carbon is having only 1/4 positive charge. That's much stable than one small carbon atom is having one full positive charge. Then what happens? Then therefore option 2 is what happens, and this is what is there. Next step is simple reaction, addition reaction. So this O minus goes and attacks here, this comes and attacks here, and you're getting this product. So the answer is option number C. Let's go once again slowly through it. Yeah. Moving to the last question. This question was very tough, okay? The correct structure that corresponds to the spectroscopy data below. So this IR they have given. So IR revealed lot of things. IR is 2720 and 1710. So 2720 is for aldehydic CHO. When you are having aldehydic CHO, this CH stretch, okay, you have to remember this hereafter. This CH stretch comes at around 2720. So very clearly we can just neglect of A and D. Apart from that, proton NMR should also shown if this COH noise should have come around 12. So you can see there is nothing around 12, whereas proton NMR it is showing that around 10 it is there. So aldehydic proton at proton NMR shows around 10. Apart from that, uh, see this peak 1710. So aldehydes show around, aldehyde COO stretch shows around 1725. But here because benzene ring is there, so benzene ring, what happens? Benzene ring will pump electron into it through plus R effect. Okay. So when it pumps electron to it through plus R effect, so this C double bond O bond becomes weaker. It gets single bond character. So when bond becomes weaker, stretching frequency will reduce, so it will come around 1710, right? Carboxylic acid actually shows, I'm not very sure where it shows. It comes much higher if I remember very well. Okay. Now let us look at the option in the NMR data. So what are the NMR data? NMR data, if you see, You are having 7.50 double doublet, 7.40 doublet, 6.90 doublet, 3.90 singlet, 3.80 singlet. Okay, so two singlets are there, that will be for CS3 very clearly. So all of them have this CS3, this and this. So very difficult to know. Aromatic peaks will give some idea. Double doublet is there, doublet is, whatever comes around 7 is generally aromatic peaks. So these are all aromatic peaks, 7.40, 7.50 and 6.90. So we have, what we are bothered about is only molecule B and C. Okay, so let's delete everything and try to see at molecule B and C. Now if you look, both of them have three protons, right? Right, now both of them have three protons, that means both can be right. Now we have to look at the splitting pattern. Splitting pattern is double doublet. So if you look at this proton, see, one double doublet is there and two doublets are there. So if you look at this proton, this will be split by this hydrogen as doublet, first doublet, and meta coupling also happens. Okay, meta coupling is around 2 hertz. So that should also show double doublet. So this proton should show double doublet and 2 hertz. I just should given actually two values. I don't know, they missed or I missed it. They should have given two values because protons, this will split into 8 protons and this will 8 hertz and this will split into 2 hertz. Yeah, they given 2. Sorry, I missed it. So it is 8 hertz and 2 hertz. So this H will be split by this hydrogen at 8 hertz, and then at beta position it will split into another 2 hertz. Let us look if any other proton is there in this also, like that. See, this proton will be doublet, this proton also will be doublet, because this proton is getting split by this hydrogen as doublet and no other hydrogens are nearby. Whereas if you look here, this proton will get split into doublet because see, here there is no hydrogen, here also there is no hydrogen. Here there is no hydrogen, but there is a hydrogen here. So it will split by this hydrogen meta hydrogen as doublet with 2 hertz. So anything like that is there? Let us look. So yeah, one proton is there like that, doublet J as 2 hertz. Let us look at this one. Now this one will split as double doublet because first it will split by this hydrogen as 8 hertz, and then it will split by this meta position. This called as W coupling. Okay, they call it W coupling, like that, W coupling. So that will be 2 hertz. So again 8 hertz and 2 hertz is seen here, and this one will be split as doublet because only neighboring this hydrogen is there, and then meta position nothing is there. Here also, or this side also ortho and meta nothing is there. So this will be split as doublet, that will be of 8 hertz, same. So here also pretty much all, not pretty much, it was splitting pattern gave exactly same for both of them. That's why I said it was very complicated. I gave up here, and it took me some time to understand what happened after that. One interesting thing is, see the hydrogens. This hydrogen is beside 2 OMe group. Now OMe withdraws electrons by minus I effect, but it pumps electrons by plus R effect. So if it pumps electrons here, you will get value because it is pumping electrons. So it is shielding this hydrogen, and this also will shield. So that means this hydrogen, so what was this hydrogen? This hydrogen is giving you doublet, that's all, right? Doublet with 2 hertz. So where is that? So this is the one, doublet with 2 hertz. Now this one uh, is shielded because extra electron, so this value should have been less than 7, but you see this is more than 7, it is 7.40. So definitely this is not the product. You can look at other things also. this hydrogen is beside CHO, right? So this should be above 7 because CHO, withdraws electrons. CHO withdraws electrons. So imagine one of the chemical structure where you are having double bond here. So this withdraws electrons here. So what happens, because that this is shielded, this should come around above 7. So this was the proton which is showing double doublet. So double doublets above 7. So this is fine. What about this? This hydrogen is beside OMe. So this should again come less than 7. So this also looks this less than 7. So everything else fits except for this proton, right? So because that we know that answer is not B, answer will be option number C. Let us look for option number C. Okay, let me delete all this stuff so that it makes more sense. Yeah, now look here. Now this one is beside CHO and OMe. In such cases what happens is CHO withdrawing group will win. It will be just above 7 actually. So if you look here, this will withdraw electron, and so this should come around 7. So this proton comes as doublet, right? Doublet with 2 hertz. So doublet with 2 hertz. Let us look here. Yeah, see this? This is coming doublet with 2 hertz. So this proton is above 7, what is seen here. What about this proton? This proton is shielded because of this OMe, right? This OMe is pumping electron. So in one of the chemical structure you can show double bond like this. So what happens is this will pump electron here, this will shield. So this should come. So this proton should come below 7. So this proton comes as, you can see here, as doublet because only one hydrogen is there. Only one hydrogen is there, and ortho, so 8 hertz. So this is the one we are talking, right? So you can see that very clearly. This is beside the OMe, so it is shielded. It is coming less than 7, doublet 2 hertz, 8 hertz. What about this? This will come as double doublet. So this is split by this 8 hertz, then split by this 2 hertz. So that's the one. That's the one. Okay. And this is again beside CHO. So of course it is deshielded, highly deshielded, and it is coming above 7, 7.50. So answer is option number C. So I'll go slowly. Please go through it. Yeah. So that's it for today's video. Thank you so very much.